um, I forgot about that cover. So I'm excited to kick off day two. Obviously, the work that we're doing here at ManTech cannot all be done with one person, and so I'm privileged to work with Ashley Birch and Michael Peters. It's just I'm here today talking about some of the work we are doing with FreeFlyer in the incorporation of its physical modeling capabilities with our digital twin development, something we call space range. And so with that, I'm going to go ahead and jump into the presentation. So the outline is to start off with some background and definitions to make sure we level set the audience with what we are talking about in terms of digital twins, virtual twins, digital threads, those kinds of things, and also talk about Space Range's history, how we got started in this development environment, and why we think it's so valuable to combine both physical models along with cyber models. We'll highlight some digital twin examples that exist in industry today, as well as a brief introduction of virtual environment options. And with the advent of cloud computing, a lot of this has become more commonplace, which gives a lot of companies and government institutions or laboratories options of how to host virtual environments so that they can make best use of their existing resources or cloud resources to suit their mission needs. And then we'll start digging into the meat of the presentation when we start looking about combining visualizations with these virtual environments and highlighting some use cases specifically for cyber-physical digital twins that we find in our work, and hopefully you will find some parallels in yours as well. And then to summarize. So let's get into it. As background, as many of you know, modern systems commonly have a multitude of interfaces that grow in scope and scale across the project. And a lot of this is due to new uses that users have with some of these modern technologies. And so the interfaces accordingly have to scale in robust ways so that they can have these pieces of technology interact in a dynamic and sometimes unpredictable way. In particular, space activities and their industries are rapidly accelerating to impact telecommunications, internet infrastructure, as well as Earth observation capabilities. And all of these things are proliferating the need for interfaces, additional modeling and simulation, robust analysis, and the potential to virtualize and test a lot of these things before you actually build hardware. And so that's what the focus of the talk today is how do we use digital twins early on in the acquisition cycle to benefit the analysis and trade studies before we actually have to build hardware. And the last big area of concern recently has been cybersecurity. As cybersecurity incidents continue, I think more and more they highlight the fact that no individuals, industries, or governments are immune to a determined adversary. And so there are some, tactical steps that both individuals and companies and organizations need to take in order to ensure that they are properly hardened against a determined adversary, as well as they understand the risks of their architecture and that it is a calculated risk they're willing to take given the need to promote and take advantage of emerging technologies for the appropriate missions. So one of the big takeaways, obviously in the bumper sticker, is that modern complex problems are truly multifaceted. And these require solutions that include not just physics modeling, but also cyber considerations in order to successfully transition these concepts into operations. So what is the difference between virtual and digital twins? And for this talk, I wanted to highlight some of this to level set everyone. And so we'll start with a virtual twin, an integrated multiphysics, multi-scale, probabilistic simulation of a 2B system that is enabled by a digital thread so that it can predict activities or performance of a 2B physical twin. So the virtual twin in this context is designed for a system that is to be built. It is not built yet, but it does so in order to predict activities and performance as that physical twin is being developed so that we can better understand its performance before the physical twin actually exists. In contrast to that, a digital twin is the same integrated multi-physics, multi-scale probabilistic simulation, but this is of an as-built system. So it uses the same best available models, sensor information, and input data, but instead of just prediction, it also mirrors the activities and performance over the life of its corresponding physical twin. So how does it do that? It actually has a real-time connection through Ethernet or wireless, et cetera, to have the inputs of the physical system feed the digital system, and the interactions of an operator of the digital system feed the physical system. So they are truly interactive and dynamically linked, so that they both sides both mirror and predict the actual performance of the system, the physical twin, as it proceeds across the life cycle. And the common thread through all of this is something that in the industry people have been talking about called a digital thread. And so for this context, a communication framework is a digital thread that allows a connected data flow as well as an integrated view of a system's data throughout its lifecycle. So this digital thread exists between different stages of development, and all of those are interconnected instead of stovepiped, so that acquirers and developers can make use of the lessons learned at each of those stages and apply those lessons across the lifecycle. And so that's where the true value of digital thread comes together, is not necessarily in any particular stage, but the interconnectedness of all the stages that provides additional insight for predictive maintenance, as well as informing the next generation of systems what needs to be built, because we know so much about the success and or failures of the existing system. So what is ManTech Space Range? You've probably heard of many cyber ranges or virtual physical environments before. ManTech started its capabilities based on this cyber range. And so it was built originally to investigate, test, and analyze and exploit cyber resiliency, specifically for information technology infrastructures. But the space range aspect was to allow it to support space systems. So with space range, we encapsulated command, control, communications, computers, and cyber architecture, or a C5 architecture, all virtually. And then with that, we incorporated space-based protocols like MIL standard 1553, and started looking at UCI, or Universal Command and Control, that allowed this virtual environment to interact with real systems with the real language they typically communicate in, all for the intent of understanding the cyber resiliency of that C5 IT architecture, so they could be more robust in the future. And starting in 2021, however, we recognized that there's a little bit of reality missing from this virtual environment. And so we started to incorporate capabilities with physics-based modeling. Specifically, we started to integrate FreeFlyer and its capabilities of how it visualized the activity of things like UAVs and satellites within the virtual environment. And we also started looking at dynamic interactions between applications that don't normally speak to one another. So say, for example, I have Cosmos command and control software from Ball Aerospace running in my environment that natively talks to a NASA satellite simulator. That's all good and fine, but what if I want FreeFlyer to visualize those interactions? I have to create a new interface for that to occur, and I'll show you a video later of how we've done that. We also got some feedback from customers desiring additional communications capabilities. So we've incorporated things like universal command and control messages, and which is a framework for anything that speaks UCI, whether it be a system, subsystem, or payload, to talk to other virtual nodes in our virtual environment. And so that's just getting started. We have an initial capability today, but we don't have all the commands that UCI is available and supporting of. So we are looking to incorporate more of that as customer insights come forward. So across industries, we see a number of digital twin examples. On the left-hand side of the chart, you see that the United States Air Force is designing and prototyping jet trainer aircraft to better inform their future pilots how to make best use of the aircraft's capabilities, and all this is done digitally. Personalized healthcare on the upper right, they are looking to see why, for example, medications fail for certain patients, and they've gotten statistics that between 40 to 70% of medications fail for many parts of the population, and the bulk of this rationale and behind the failure is due to the genetic makeup of the patient itself. And so what healthcare providers are looking at today are creating digital twins of the patients so they can test some of the interactions of the medications with the digital twin before they actually administer it to the physical counterpart. And so these days are coming in terms of how we make use of digital twins, not just in industrial and manufacturing applications, but also in everyday life applications for personalized healthcare. And in the lower right, we see a graphic of the Port of Antwerp. This is an excerpt from a video that's actually on YouTube, where the city of Antwerp has invested in a digital twin to monitor the activities of the entire port. So they have environmental sensors, they have drones that can surveil the port, they have a command and control central hub that can manipulate each of these items and redirect them as necessary to make sure they understand everything that's going on in the port, where a crane might be broken, where some effusions or emissions from a container ship are beyond normal, and they might be able to alert, like the Coast Guard, for example, that something anomalous might be going on with their engine before they actually leave port. So all of this exists due to the investment in infrastructure by the city of Antwerp, all to facilitate better port operations in that area. And so all of these digital twin examples are at various levels of maturity, right? But it does show the promise and breadth that digital twins can bring to a variety of industries. So here I wanted to highlight just briefly some of the virtual environment options that are available for creating virtual environments. So on the left-hand side, we see a graphic where the application layer is separated from the infrastructure layer through this control layer. And this is the classic software-defined networking, which allows users to dynamically and efficiently configure networks in cost-effective fashions. And by doing so, it allows them to really take advantage of cloud architectures. On the right-hand side of the screen, we have something called a software-defined infrastructure. And this is where ManTech has chosen to go, in addition to a number of government laboratories and industry partners. This environment allows not just the compute resources to be virtualized, but also storage and networking resources. And so all of this creates a novel policy-based infrastructure that allows provisioning across each of these software-defined infrastructures to make better use of cloud capabilities, in addition to allowing some of these to be hosted on-prem or across multiple clouds. So this flexibility has been valuable in our studies, so that customers can kind of dictate where they want their environment to be housed. They can also take advantage of environments where I might have a prime contractor want to expose some virtual machines to a subcontractor, and they can do that because of this policy-based provisioning in a much more robust way than they could do before. So moving forward, I wanted to highlight a little bit about the visualizations, as well as how you can do that within the virtual environment. And there's a video here that I will show for you that highlights some of the capabilities we've been doing at ManTech relative to the simulations and such that we've been working on. In particular, we have a UAV scenario in FreeFlyer that allows us to interact with it in a more dynamic way. And so as this shows, I'll talk a little bit about why this virtualization is beneficial to our missions. So we've always valued the inputs and flexibility of FreeFlyer, and more importantly, that the physics embedded within the software allows our users to trust what they are seeing, as well as trust the insights they are gaining from these kinds of visualizations. And so this has been very important for customer acceptance of these kinds of environments, knowing that the physics behind the simulation is true, as so that we could better understand the interactions of things like Kepler and Bernoulli in advanced and dynamic ways. The aspect that we are incorporating within ManTech Space Range is the cyber threat modeling. And while we have not had as many strides forward as what FreeFlyer has done in its subsequent versions, we do recognize that the visualization of these activities needs some more development and some customer feedback. But the value of having an environment that allows you to do virtual cyber and physics-based modeling, and the interactions between those, so we can better understand when the physics affects the cyber and when the cyber affects the physics, is truly unique. And we find that to be a much better approach overall, because then I don't have to worry about multiple environments to investigate both domains. I can use a single environment for all those domains. And then last but not least, we've been looking at how to host these capabilities on a cost-effective, scalable infrastructure like clouds, right? So containerization is always a topic of interest. And some of these user interfaces of physics-based models, such as FreeFlyer, they can be containerized, but it's not as user-friendly when you want to expose some of the flexibility of the software within the container. And so we're still working amongst ourselves about how do we do this in the most effective fashion. What we have started to do, however, is to make full advantage of the software as it exists, is just to have that software running in a dedicated container, and then we just launch multiple containers as we need to interact with the different free flyer engines that we would use. And so in this way, by combining cyber and physical models in this common virtual environment, we truly believe that this provides our customers as well as ourselves for our own analysis, a robust and holistic approach for digital twins and for them to express their utility to a variety of missions. So here are a couple of use cases that we have highlighted in our analysis for you today. And obviously there's going to be more as your questions and customer questions continue to come in. First and foremost, on the upper left is the mission integration testbed. And within this environment, we can incorporate new pieces of software or patches, new hardware, new network architectures, and we can do all of this virtually. So we can test to see what the impact is to mission before we actually have to deploy this operationally. So this provides us a lot of flexibility to optimize prior to deployment so that we really can believe and trust that what we produce for the field is going to be effective and work the very first time out of the box. We're not going to have to do any rework by testing it in this digital twin kind of construct. On the right, we talk about a space system digital twin. And here we start talking about a network topology, say, for example, in this SDI that has a satellite ground station, but that also have virtual satellites, where these virtual satellites actually have a digital connection to their physical counterparts. And likewise, the virtual satellite ground station has its connections to the physical ground station architecture. And so they're truly interactive, and you can think of it almost as a continuity of operations type of construct where the digital twin can actually start to manipulate the physical satellites and the operational software that runs in the ground station can start to manipulate the virtual satellites. There shouldn't be any difference from their perspective because they're just interacting with a node. And by having a digital twin of this, we have a more robust way of picking out courses of action should something anomalous go on. We also have ways of doing more robust on-the-job training, whether it be Space Force Guardian or a commercial satellite operator. You'll be using the same software, just one will be in the virtual environment and one will be in the physical environment. On the lower right, we talk about a space cyber test range. And so here we're actually looking at the cyber resiliency and or vulnerabilities of this architecture, as well as the satellites themselves, to understand where the threat vectors are relative to cyber adversaries and how to harden those. And so this virtual environment allows us to investigate not just the interfaces, but the physical hardware and identify what those vulnerabilities are so we can actually impose new restrictions or mitigations to thwart any potential adversarial attack. Similarly, if you wanted to have a gold standard of your C5 architecture in the virtual world, then you could run scans on the physical infrastructure and compare it to the scans you would run on the digital architecture. And if there's a difference, something has happened, whether it be on purpose or by accident or by an adversary. And by having a gold standard in the virtual world, which is completely under your control, and comparing it to a physical scan that is occurring in operations, you can have a much more robust and autonomous way of ensuring your cyber resiliency posture is as strong as it could possibly be. And last but not least, we have a box about multi-domain analysis and ConOps. And this is an allusion to the fact that, by having this virtual environment that allows us to do not just physical modeling, but cyber modeling and assessments, we have a truly multi-domain analysis framework from which we can look at all the different domains: cyber, space, air, land, surface, subsurface. All of these things can be virtualized so that you can better understand how each of these strengths can come to play in a multi-domain conflict so that we would have an upper hand over any adversary because of the information dominance we would have by doing the multi-domain analysis and comms development in advance of the conflict. And so last but not least, I wanted to show a little bit of a video of what we were talking about in terms of having Free Flyer interact with command and control software from Ball Aerospace. So in this scenario, many of you might have seen it before. We have a slew maneuver that we've adapted by using Cosmos. And so this image satellite is collecting over the continental US, and it will slew between different cities as it collects. It will be interspersed with some blue text, and that is where we are actually sending a command from Cosmos to FreeFlyer to execute a different command that wasn't native to this slew maneuver scenario. So this first one is going to be a no-op maneuver, with basically a command to the satellite. I'm not going to ask you to do anything yet, but I want to make sure that you're listening to me. And so there it goes, it's executing a no-op command, and now it's going to slew to Louisville, right? The next one is going to look at a image collection, and it dictates the size of that image collection as it slews down to Atlanta. And there's also a hardware checkout command prior to that image collection. So all of these commands were actually, the blue ones were sent by Cosmos to FreeFlyer, and we had this communication architecture that allows us to take the translated Cosmos command and into a way that FreeFlyer would understand and then make use of in support of this scenario. So in summary, I wanted to, reiterate our recognition and our support of, additional robust modeling, simulation, and analysis capabilities. We are truly seeing this across the customer front that, the demand for this has never been stronger. And there's truly a need for things like standards for improved interoperability of modeling and visualizations in addition to digital twins. And that, in particular, ManTech cyber physical digital twin. This kind of environment does truly support a variety of customer use cases, as we've highlighted, because of this flexibility and customization. And so it's almost unlimited in terms of what we can virtualize and how we can analyze this. So it's up to the customers as well as industry partners and their imagination of what might be missing. For example, one of the things that we were asked about recently was about a real-time operating system and whether or not our virtual environment can support it. And we've done some research and we can. And so that's one of the things we're looking at maybe later on in 2022 is the incorporation of real-time operating systems within the virtual environment as well. So we could actually, run the VxWorks or the RTEM software that be running on board the satellite in the virtual environment. And last but not least, the benefit of combining both cyber and physical models and analysis capabilities is truly increasing and is becoming the cornerstone of our number of different trade studies and ConOps development efforts that we are seeing. And so I appreciate all of your time and attending today, and I look forward to any questions. And if I can't get to them today online, I'll be happy to follow up with, with you individually.
Yeah, thanks so much, Stephen, for a great presentation. It sounds like ManTech really is developing a great digital twin solutions. We do have a couple questions for you. First up is, are there foundational technologies for creating a digital twin that are used across different industries, whether that be healthcare, aviation, or the port modeling that you described, or are there digital twin systems created from scratch for each implementation?
Yeah, that's a great question. I think it depends on the provider. What we have seen is that many folks are taking advantage of industry standard tools like Ansible or Terraform and those kinds of things, so they could actually host things more dynamically in a cloud-like environment. And that's what we're doing as well. We have seen others that are looking more at custom solutions that might be more intertwined, but because of that, you might be buying into a more limited solution because of that proprietary nature.
Gotcha, that's great. And the next a question is, how does the move, at least in the commercial space, towards ground stations as a service or even mission operations as a service impact how you might build and utilize these digital twins?
That's interesting too. Yeah, so we've been thinking about that ourselves. One of the things that we are looking as an augmentation to those is the whole cyber aspect, because a lot of those capabilities don't incorporate or are hardened relative to the way we would typically want to do it ourselves, being a cyber-focused company. So that's one detail that I think, having such an environment to enhance what a ground station as a service or a satellite as a service or whatever it might be, this environment would add to that to augment the existing system they have, whether it be legacy or new, so that they can incorporate the cyber resiliency aspect in addition to the ones they already have for physics and others.